It's September 15th, 1916. Flers-Courcelette, France. The British Mark I tank, all 28 tons of it, is grinding toward German trenches at 3.7 miles per hour, walking speed. Inside, 8 men are crammed into a steel box where the temperature hits 120 degrees Fahrenheit. The noise is deafening. Exhaust fumes are choking them. But none of that matters because they're about to hit a problem that'll stop the entire tank program dead. The trench. German trenches at the Somme average 8 feet wide. Some are 10 feet. The Mark I's tracks are 26 feet 5 inches long. On paper, the math works. The tank should cross easily. The tracks extend far enough forward and back to bridge the gap while maintaining contact with both sides. Except the math is wrong. When the Mark I reaches the trench, the front tips down into the gap. The tracks keep moving, but they're churning air. The rear tracks lose traction as the tank's weight shifts forward. The whole machine tilts nose down at a 45-degree angle, engine screaming, going nowhere. The crew has about 30 seconds before German artillery zeroes in on this immobile 28-ton target. Of the 49 Mark I tanks deployed at Flers-Courcelette, 17 break down before reaching German lines. Another 9 get stuck in trenches. That's 26 tanks out of commission, a 53% failure rate. And trench crossing is the primary culprit. British Tank Corps commanders are furious. They'd promised high command that tanks would break the stalemate on the Western Front. Instead, they've delivered expensive metal coffins that can't cross the one obstacle they were specifically designed to defeat. The problem isn't the crew. It's not tactics. It's pure physics. The Mark I's track length-to-width ratio is wrong. At 26 feet 5 inches long and only 20 inches wide, the tracks don't distribute weight properly when bridging gaps. The center of gravity shifts too far forward during descent. Once that happens, the rear tracks lift off the ground and lose all traction. Back in London, the Landships Committee, the government body overseeing tank development, is in crisis mode. They've spent $1 million on tank production. That's roughly $50 million in today's currency. The Mark I went into production in March 1916 with 150 units ordered. Now, 6 months later, they have a weapon that works beautifully on flat ground and fails catastrophically at the exact moment it's needed most. Winston Churchill, who championed the tank program as First Lord of the Admiralty, is demanding solutions. Field commanders are threatening to abandon tanks entirely. The Germans are already reverse engineering captured Mark I tanks and designing anti-tank tactics. Here's what makes this worse. The German trenches are getting wider. Intelligence reports from November 1916 indicate German engineers are deliberately expanding trench systems to 12 feet wide specifically to defeat British tanks. They've seen the Mark I struggle with 8-foot trenches. They're betting that 12 feet will stop them completely. They're right. The Mark I cannot cross a 12-foot trench. Mathematically impossible with the existing track design. The British have 6 months, maybe less, to solve this problem before the Germans finish widening their defensive lines across the entire Western Front. If they can't, the tank program is finished. 3 years of development, millions of pounds, and the hopes of breaking trench warfare stalemate. All gone. What nobody at the Landships Committee realizes yet is that one engineer has already figured out the solution. His name is William Tritton, and he's about to redesign tank tracks in a way that'll seem physically impossible until the moment it works. Real quick before we dive in, drop a comment and let me know where you're watching from. What city, what state, what country? And hey, what time is it where you are? Always cool to see how global this audience is. All right, let's get into it. William Tritton isn't a military man. He's the managing director of William Foster & Company, an agricultural machinery company in Lincoln, England. Before the war, his company built tractors and steam engines. Now he's building tanks. But the Mark I disaster at Flers-Courcelette has exposed a fundamental flaw in his design. The physics problem is brutally simple. When a tracked vehicle approaches a trench, three things happen. First, the front of the track descends into the gap. Second, the vehicle's center of gravity shifts forward as more weight transfers onto the descending track section. Third, and this is where everything fails, the rear track section lifts off the ground as the vehicle pivots on the forward edge of the trench. Once the rear loses contact with the ground, you have zero traction. The front tracks are suspended in air over the trench. The rear tracks are spinning uselessly. The tank is stuck, tilted forward at 40 to 50 degrees, perfectly exposed to enemy fire. Major Walter Gordon Wilson, Tritton's co-designer on the Mark I, has the math. For a tracked vehicle to successfully cross a trench, the track length must be at least 1.5 times the trench width. That's the minimum ratio needed to maintain rear track contact while the front crosses. The Mark I's tracks are 26 feet 5 inches long. Using Wilson's formula, that gives a maximum crossing width of 17.6 feet. Except that's theoretical maximum. In real-world conditions, muddy ground, shell craters, debris-filled trenches, you need at least a 2.1 ratio for reliable crossing. That means the Mark I can only reliably cross 13-foot trenches. German trenches are being widened to 12 feet right now. By spring 1917, intelligence estimates they'll hit 14 feet in key sectors. Some will go wider. The British Army's solution? Make the tracks longer. Simple, right? Wrong. Lieutenant Colonel Ernest Swinton, the tank program's military advisor, proposes extending the Mark I's tracks to 35 feet. That would handle 17-foot trenches with the 2.1 safety ratio. The Landships Committee approves the modification in October 1916. Tritton runs the numbers and immediately sees the problem. A 35-foot track adds 3.2 tons to the vehicle's weight. The Mark I's engine, a Daimler six-cylinder producing 105 horsepower, is already running at maximum capacity to move 28 tons. Adding another 3.2 tons means the top speed drops from 3.7 mph to roughly 2.8 mph. That's slower than walking speed. Worse, the longer tracks increase ground pressure unevenly. The Mark I already sinks 8 inches into soft ground. Longer tracks mean more surface area, but the weight distribution becomes unstable. The vehicle bogs down in mud, which covers 60% of the Western Front from October through April. The mechanical stress is even worse. The Mark I's track system uses 90 track plates connected by pins. Each plate weighs 35 pounds. Extending to 35 feet means adding 30 more plates, over 1,000 pounds of additional rotating mass. The drive sprockets, the geared wheels that move the tracks, aren't designed for that load. Field tests in November 1916 show the sprockets failing after 15 miles. The bearing assemblies overheat. Track pins shear off under stress. France tries a different approach. Their Schneider CA-1 tank, deployed in April 1917, uses shorter tracks, but adds a forward-mounted tail skid, a metal frame that extends behind the tank to provide support during trench crossing. It works on 6-foot trenches. At 8 feet, the tail catches on the far side of the trench, and the tank high centers, belly stuck on the trench edge, tracks spinning in mid-air. The Americans aren't helping either. The U.S. Army's Holt tractor, which inspired the original tank track design, can't cross trenches wider than 5 feet. The U.S. won't enter the war until April 1917 anyway, so their input is theoretical at best. By December 1916, the Landships Committee has tested 6 different track modifications. All fail. Longer tracks bog down or break. Wider tracks add too much weight. Reinforced tracks snap under lateral stress. Special grip patterns improve traction, but do nothing for trench crossing. The Germans, meanwhile, are laughing. Captured German intelligence reports from January 1917 refer to British tanks as mobile coffins and trench gifts, vehicles that helpfully get stuck where German artillery can destroy them at leisure. Field Marshal Douglas Haig needs a solution by March 1917. That's when the British offensive at Arras is scheduled to begin. He's promised 60 tanks for the assault. If those tanks can't cross German trenches, the offensive fails before it starts. Tritton has 10 weeks to solve a physics problem that stumped every engineer who's looked at it. January 1917. William Tritton is staring at a wooden model of a tank in his Lincoln workshop. He's been staring at it for 3 days. The Landships Committee wants longer tracks. Haig wants faster tanks. Wilson wants more engine power. Everyone wants something different, and none of it works. Then Tritton stops thinking about tracks and starts thinking about geometry. The problem isn't track length, it's track shape. Every tank designer since 1915 has used the same basic track configuration, a rectangular loop running parallel to the ground. Flat top, flat bottom. The tracks run under the hull in a straight line. It's the obvious design. It's also wrong. Tritton sketches a new shape. Instead of rectangular tracks running under the hull, what if the tracks ran around the hull? Not underneath, around. He draws a rhomboid shape. The tracks start at the front of the vehicle, curve up and over the top of the hull, then down the back. The entire hull sits inside the track loop. His engineering team thinks he's lost his mind. Major Wilson reviews the sketch and lists 12 reasons it won't work. The tracks would have to be 26 feet 5 inches long just to wrap around a hull that's only 14 feet long. The weight distribution would be insane. The drive system would need complete redesign. The suspension geometry makes no sense. Tritton builds a wooden mock-up anyway. He uses his Mark I prototype, nicknamed Mother, as the base. He removes the existing tracks and builds a wooden frame showing the new track path. The frame curves up from the front, reaches maximum height at the midpoint, then curves down to the rear. The geometry is radical. Instead of the tank's center of gravity sitting above the tracks, it sits inside them. The tracks don't support the hull from below, they wrap around it. When this tank approaches a trench, the forward section of track descends into the gap, while the rear section, which curves up and over the hull, maintains ground contact for an additional 8 feet behind the vehicle's center point. Wilson does the math. This design extends the effective wheelbase from 17 feet to 26 feet 5 inches, the full length of the tracks. Using the 2.1 safety ratio, that's a reliable crossing width of 13.2 feet. The Germans are widening trenches to 12 feet. This design beats them with 1.2 feet to spare. But here's the real genius. The rhomboid shape doesn't just extend the wheelbase, it changes how the tank crosses trenches entirely. When the front dips into a trench, the rear tracks don't lift off the ground because they're positioned 9 feet further back than they would be on a conventional design. The center of gravity stays inside the track loop. The physics problem that killed the Mark I simply doesn't exist anymore. Tritton presents the design to the Landships Committee on January 19, 1917. They reject it. Too radical, too risky. Production would require retooling the entire factory. The military wants incremental improvements, not revolutionary redesigns. Winston Churchill overrules them. He's no longer First Lord of the Admiralty. He resigned after the Gallipoli disaster. But he's still in Parliament, and still pushing the tank program. Churchill sees Tritton's drawings and immediately grasps what the Landships Committee missed. This isn't just a better tank. It's a different weapon entirely. Churchill gets Tritton authorization to build a prototype. 1 tank. If it works, they'll proceed to production. If it fails, the tank program reverts to modified Mark I's designs. Tritton has 6 weeks. His team at William Foster & Copers works 16-hour shifts. They can't use the existing Mark I hull. It's too tall for the rhomboid track configuration. They design a new hull from scratch, lower, wider, with a flattened roof and sponsons that mount the guns outside the track path. The hull is 13 feet 9 inches long, 13 feet 6 inches wide, and only 8 feet 2 inches tall. It's 4 feet shorter than the Mark I. The tracks are the real challenge. The curvature means every track plate has to be precisely angled. The drive sprockets need repositioning to the rear of the vehicle. The suspension system, which previously used unsprung rollers, needs complete redesign to handle the weight distribution of the rhomboid shape. On February 28, 1917, the prototype rolls out of Foster & Coer's factory in Lincoln. It weighs 28 tons, exactly the same as the Mark I, but it looks completely different. The rhomboid shape makes it look like a mobile fortress, with tracks that seem to wrap around empty space. They call it the Mark IV, and tomorrow they're taking it to a 12-foot trench. March 1, 1917. Burton Park, testing grounds, 15 miles south of Lincoln. The British Army has dug a trench specifically for this test, 12 feet wide, 8 feet deep, with vertical walls. This is the exact specification of the widened German defensive trenches reported by intelligence. If the Mark IV can't cross this, the entire rhomboid design is worthless. Present for the test: Major Walter Wilson, Lieutenant Colonel Ernest Swinton, 3 members of the Land Ships Committee, and a dozen skeptical Army officers who've already written off the tank program as a failed experiment. William Tritton climbs into the commander's position. The Mark IV's crew compartment is cramped, but better ventilated than the Mark I. The driver sits front left, Tritton behind him. The Daimler 105 horsepower engine rumbles to life. Exhaust fumes fill the cabin immediately. That part hasn't improved. The tank lurches forward at 3.8 mph, slightly faster than the Mark I despite identical weight and engine. The rhomboid tracks distribute ground pressure more evenly, 12.6 pounds per square inch compared to the Mark I's 14.2 psi. Less ground pressure means less resistance, which means fractionally better speed. They approach the trench at a 90-degree angle. This is the hardest crossing scenario. Coming in at an angle makes it easier because the tank bridges the gap diagonally, reducing effective width. But the Army wants to see if the Mark IV can cross head-on, the way it'll have to in actual combat when German machine guns force a direct assault. 50 feet from the trench. The observers can see the rhomboid tracks clearly now. The front sections are already angled downward, following the curve of the hull. The rear sections arc upward and over the engine compartment. 30 feet. Tritton doesn't slow down. You need momentum for trench crossing. If the tracks stop moving, even for a second, the tank settles into the mud and you're stuck. 10 feet. The front track sections hit the edge of the trench and drop. The nose of the Mark IV pitches forward at 35 degrees. Inside, Tritton braces against the commander's position. The engine note doesn't change, still pulling full power. This is the moment where the Mark I fails. Front tracks drop into the trench, rear tracks lift off the ground, the whole vehicle pivots forward and stalls. Not the Mark IV. The front tracks descend into the trench, but because they curve up and over the hull, the rear track sections are still 26 feet behind the front edge. The rear tracks maintain full ground contact. The engine keeps pulling. The center of gravity stays inside the track loop. The Mark IV's nose drops until it's 45 degrees down. The front tracks hit the far wall of the trench and start climbing. The entire vehicle is bridging the 12-foot gap now. Front tracks on the far side, rear tracks on the near side, belly suspended over empty space. 5 seconds. That's how long the Mark IV spends crossing the trench. The front tracks claw up the far wall, dragging 28 tons of steel tank behind them. The rear tracks maintain traction. The hull rises. The angle decreases from 45 degrees to 30, then 15. The Mark IV levels out on the far side of the trench. Total crossing time, 8 seconds from edge to edge. 0 hesitation, 0 loss of traction. The engine never strained. The tracks never slipped. Tritton orders the driver to reverse. They're going to cross it again, backward, just to prove it wasn't luck. The Mark IV backs up, rear tracks first into the trench. Same result. 8 seconds. Perfect crossing. The rhomboid geometry works in both directions because the track configuration is symmetrical. The observers are silent. Swinton breaks the silence first. Do it again. Faster. Third crossing. The driver pushes to 4 mph torch, the Mark IV's maximum speed. Same result. The increased momentum actually helps. The tank bounces slightly as the front tracks hit the far wall, but maintains traction throughout. Fourth crossing. Oblique angle, 45 degrees off perpendicular. The effective trench width increases to 17 feet because of the diagonal approach. The Mark IV crosses it without hesitation. The longer effective wheelbase of the rhomboid design compensates for the increased gap width. Wilson is calculating on paper. He looks up. It'll cross 14 feet, maybe 15 if the ground is firm. Tritton climbs out of the tank. How many do you want? The Landships Committee authorizes production of 1,220 Mark IV tanks on March 3, 1917, 2 days after the successful test. The order includes 595 male variants mounting 2 6-pounder guns and 625 female variants with machine guns only. Production begins immediately at William Foster and Company and Metropolitan Carriage, Wagon and Finance Company in Birmingham. The first Mark IVs reach France in April 1917, just in time for the Arras offensive. They face the widened German trenches everyone has been worried about. The trenches are 12 feet wide. The Mark IV crosses them on the first try, every single one. The Battle of Arras begins on April 9, 1917. 60 Mark IV tanks roll toward German lines near Monchy-le-Preux. The Germans have spent 4 months widening their trenches. They're confident. British intelligence has reported the Mark I's trench crossing failures at the Somme. The Germans believe their 12-foot trenches are tank-proof. They're wrong. The Mark IVs cross the first trench line without a single failure. German defenders watch 28-ton steel machines drop into trenches that should stop them, then climb out the other side and keep coming. The psychological impact is immediate. German infantry abandon their positions. Machine gun crews retreat to secondary lines. The Mark IVs advance 3.5 miles on the first day, the deepest British penetration since trench warfare began in 1914. Of the 60 Mark IVs deployed at Arras, 54 successfully engage German positions. The 6 failures are mechanical breakdowns, engine problems, thrown tracks, nothing related to trench crossing. That's a 90% operational success rate compared to the Mark I's 47% at Flers-Courcelette. The rhomboid track design doesn't just work. It redefines what tanks can do. British commanders start planning operations around trench systems they previously considered impassable. The Mark IV can cross 12-foot trenches, crush barbed wire 30 yards deep, and shrug off rifle and machine gun fire. German defensive doctrine, built entirely around stopping infantry assaults, has no answer for it. By June 1917, the Germans are redesigning their defensive systems. They stop widening trenches and start digging them deeper with steeper walls. They develop the first dedicated anti-tank weapons, modified 70-mm field guns, firing armor-piercing rounds at point-blank range. They create the first anti-tank rifle, the Mauser 1918 T-Gewehr, a 13-mm bolt-action rifle specifically designed to penetrate tank armor. None of it stops the Mark IV. The tank participates in every major British offensive from Arras through the end of the war. At the Battle of Cambrai in November 1917, 476 Mark IVs break through the German Hindenburg Line, considered the strongest defensive position on the Western Front. They advance 5 miles in 6 hours, something British infantry failed to achieve in 3 years of trying. Tritton's rhomboid design becomes the standard for British tank development. The Mark V, introduced in 1918, uses the same track configuration. So does the Mark 8 Liberty tank, a joint British-American design that remains in service until 1932. The Americans adopt the rhomboid principle for their own tank program. When the U.S. enters the war in April 1917, they have 0 combat tanks. By 1918, they're producing the M1917 light tank based on the French Renault FT, but their heavy tank program copies the Mark IV's track geometry directly. The French experiment with rhomboid tracks on the Char 2C super heavy tank, developed in 1917 but not deployed until 1921. At 69 tons with tracks 33 feet long, the Char 2C can cross 13-foot trenches, a direct application of Tritton's geometry principles scaled up for a heavier vehicle. Post-war, the rhomboid configuration falls out of favor. By 1920, military doctrine has shifted. Trenches are no longer the dominant battlefield obstacle. Tank designers prioritize speed and maneuverability over trench crossing ability. Modern tank track designs return to conventional rectangular configurations running under the hull. But Tritton's fundamental insight remains. He proved that track geometry, not just track length, determines obstacle crossing capability. Modern armored vehicle designers still use variations of his principles. The center of gravity relative to the track contact patch, the wheelbase to obstacle ratio, the distribution of ground pressure. These are still primary considerations in tracked vehicle design. William Tritton receives a knighthood in 1917 for his tank development work. He continues designing armored vehicles through the 1920s before returning to agricultural machinery. He dies in 1946 at age 79. The Mark IV remains in British service until 1920. Total production reaches 1,120 units, making it the most produced tank of World War I. 8 Mark IVs survive today in museums worldwide, including one at the Tank Museum in Bovington, England. The military lesson is permanent. Tactical problems require engineering solutions, not just tactical adjustments. The British tried longer tracks, more powerful engines, better crew training, all incremental improvements to a flawed design. Tritton solved the problem by changing the fundamental geometry. He didn't make the tank better at crossing trenches. He made the tank physically incapable of getting stuck. That's the difference between iteration and innovation. And in March 1917, facing a 12-foot trench at Burton Park, innovation won on the first try.